In this video, we'll begin our discussion of section 13.1. This is our introduction to multivariable functions. We are going to start moving into three dimensions with just an x, y, and z, and start talking about graphing, and then we're going to start doing calculus on three dimensions. First thing I want to talk about is understanding the dimensions that we get from an expression. So the first thing I want to point out here is if we want to graph a function, we can actually look at the function itself and determine how many dimensions. The rule here is you must have one dimension more than the number of independent variables. You are already used to this. Consider this function, 2x minus 3, right? This is graphed in, it's a line, it's graphed in two dimensions. Now notice though, there is only one variable. A good place to tell is right here. Only one variable, so one more tells me it's in 2D. Now where we're headed is taking, let's not call it f, let's call it g of xy, and let's just make up some function, x squared minus 3y squared. All right, this is in, I have two variables, right? Two variables here. So that tells me this is in 3D, just like the extension from one variable to 2D. And then the furthest we're going to go is three variables. And actually, there will be four with our independent or our dependent. Let's make one up here, 2x squared minus y over z minus 3. Okay, this has three variables, so this is going to be graphed in 4D, whatever that may be, right? Good luck trying to figure out what that is, right? We have plenty of theories and people going about it. We're not going to worry about that. All we know is if I were to graph that, I would take three variables and my graph would end up in 4D, whatever that would look like. Now, what we're more, I think that is more interesting to us when we're going to graph a function, because we need to know what numbers we can plug in, we're actually going to graph the domain too. You guys have done this as well in college algebra. Take the function f of x, right? And let's call it something, let's say, okay, 1 over the square root of x, right? The domain for this is 0 to infinity with open brackets, right? This is one dimension, right? And it's only going from 0 to infinity. There is no y direction. It's just x. Those are the x's I can plug in. Now, that extends, though, to when we have two variables, because now we're not only dealing with some function of x or just y, we're going to have multiple, so the domain here is going to be in 2D. All right, sorry for the dash there. I changed my notation in the middle. That's in 2D, right? And then if we were to keep going with an h function with x, y, and z, whatever that may look like, the domain for that is going to be in 3D. So we have two different rules. This is one more, and then this one is the same as the variables. So if we want to graph a function, we add one more dimension to the number of variables, and that tells us how many dimensions we're going to have. And then to graph the domain, we do the same number of variables as dimension. All right, let's discuss this function here. Some of you guys, this may be the first time you've ever seen a triple pair, or triple, it's not a pair then, a triple order here. My brain just blanked on what that's called, but we have three variables, and we're going to plug all three in and get a fourth number. We're just going to discuss here because I just want to make sure you understand each part. Let's talk about there are three variables, so that means this graph is in 4D. So let's write that down. Sorry, my notes are all over the place. 4D graph, whatever that may look like, we can state it. We're not going to graph it though. And then 3D domain. So that means when I find my domain, I'm going to find a set of x, y's, and z's that work, right? It's going to be some surface, some picture that I can pick any triple coordinate out of that surface, and it will be part of the domain. That will become more clear with some of the pictures that we're going to draw. Okay, another thing I want to just make sure we understand is what does plugging a point in look like this? We'd have a x, y, and a z. We'd have all three, and we would just plug them in. Nothing new here. This shouldn't be surprising. But just to make sure that you understand how, if I have multiple inputs, how I plug those in, we end up getting the square root of 11. Whatever this may be, this means I picked a point in space, right? In 3D space, 0, 2, -1, in space, whatever that may be, it maps to square root of 11. You already do this kind of stuff. If you think about this, volume is length times width, right, times height. 3 variables, you would plug them in, you would get a fourth number. We do this a lot of the time, we just don't think about it in graphs. So it took 3 variables and gave 1 output. Right. One other thing I do want to just go ahead and use this time to practice is if we had to plug in compositions. So that's some function of u, probably some function of x, maybe, we don't know. And what if we had to plug all this in? Well, this is the algebra stuff that kind of gets people. I got plus 2 times u minus 1 squared plus 3u plus 1 squared. I'm going to do this pretty quick, so if you need to distribute or FOIL, I hate that term, but if you need to FOIL, please do so. You can pause. I'm going to jump forward. I've done so many FOIL stuff that this is pretty straightforward. Okay, so we have that. It can be reduced down to, sorry for my bad handwriting here, but 6u squared plus 2u plus 5. We can stop. All I wanted to do on that one is just practice doing a composition. I just want you to know the 4D graph, the 3D domain. That's going to be very good insight for us going forward to know that. And then we need to be able to plug points in, and we also need to be able to do compositions. What compositions are is plugging a function into another function. All right, let's take a look at this example. We are going to find the domain and range. The good thing is you look for the exact same things that you did in pre-calc. You do the same things you did in calc. You're looking for trouble spots. Well, x times y, that's no problem. I can take any two numbers, even if it's 0, and multiply. But I do have a denominator. And we know denominators cannot be equal to 0. Right? That tells me that x cannot equal y. I can pick any point I want as long as x and y they're not equal. So the domain, how we write this, you're going to write it like this a whole lot. We open a set. And these are the set of ordered pairs, x, y. That straight line means such that. Let's write that in. Such that. So the set of ordered pairs such that x doesn't equal y. That's all it says. Set of ordered pairs such that x doesn't equal y. I actually just remember the phrase I was trying to think of earlier with this up here. That is a ordered triple. It's a way to say it. Like that, the 3 points right here, this XYZ is an ordered triple. Like an ordered pair, but ordered triple. Pair doesn't work because pair means 2. Don't know why my brain blanked on that, but it did. All right, they asked for domain and range. On this one, I just don't see any trouble spots, meaning, okay, I can make x minus y anything I want. I can make x, y. I can pick anything I'm wanting to come out of this. So the range, okay, well, the range is one variable. It's an output. We'll call it z. So the set of numbers z such that z is between negative infinity and positive infinity. I can get whatever I want out of this function. This one's a little clear. The ones that you're going to have to do more will be more obvious. Let's take a look at something where that is the case. So this is domain and range. Where we're headed is you're going to eventually graph the domain of these. So we'll get to that in this section. This example says find the domain and range of that function. Okay, so I know that integrand there, 4 minus x squared minus y squared. I know that has to be, okay, I'm taking the square root, so it has to be bigger than 0. It can also be 0 itself. I'm going to manipulate this. This is x squared plus y squared, just with a negative distributed through. The reason is now I'm going to add that whole parentheses to the other side. So we get 4 minus less than or equal to x squared plus y squared. I'm going to flip this over. We know this is less than 4. That's a circle, right? Hopefully you see that right away. We circle with a radius of 2. And this says, hey, if you pick any ordered pair that's on that circle or inside that circle, right? That's what the less than means. On the circle or less than circle. I also, and this is obvious, but I'm going to write it here because it's going to help us do something in a minute. This has to be bigger than 0. That's totally obvious because they're squares, right? They'll never get a negative. We don't even have to really write that. But I'm going to use it here. So let's write our domain. It's the set of ordered pairs. We don't just have one number now, such that 0 is less than or equal to x squared plus y squared, less than 4. What we're saying is all ordered pairs inside or on the boundary of that circle. Okay, the reason I put the 0 here is I want to think of my function now. I'm going to rewrite it real quick like this. All right, let's talk about the range. This is the numbers that are coming out. So a z such that, okay, well, the biggest this inside can be, let me highlight that. The biggest this can be is a 4. All right, let's do smallest first. The smallest it can be is a 0. It's right here, right? So that would be the square root of 4, which is 2. So I know that the range will go from 2. Okay, let's talk about if that was the biggest it could be. Well, the biggest it can be is 4. So 4 minus 4, right, highlighter, is the square root of 0, which is 0. So I know my range is from 0 to 2. All I did is I plugged this value in and I plugged this value in because I know that the x squared plus y squared is caught between 0 and 4. It can't be outside of that, which tells me my range. That's why I put the 0 there. We don't have to put the 0, but it tells me exactly what to plug in. What value will it be the smallest and what value will it be the biggest? All right, we are going to start graphing these domains. So let's take a look at an example. This note here, to graph a domain, we must have an axis for each independent variable. Let me show you what that means. Consider this function. Right? We know that the denominator x can't be negative, and also can't be 0. So the domain here is, okay, I could put it on a number line, and I could put my 0, and the way I graph it is I say, okay, parentheses here because it can't be 0, and it goes on that way. So my domain, right, is in one dimension. It's the same amount of variables that I have. If I have an x, one variable, then my domain is in one dimension. If I have two variables, it's going to be in two dimension. Okay, so answering that, with that in mind, I mean, example, find and graph the domain of this function. Okay, so the graph is in 3D graph, and then there are only two variables, so 2D domain. We want to find the domain and graph it. Okay, so this top here, and we're looking for problems. X, Y can be fine. That's fine. It can be anything it wants. It can be 0. It's in the numerator. But the x squared minus y squared cannot be 0. Now, we can take this further. X squared cannot equal y squared by just adding it over. Now, taking the square root, I'm going to put the y over here. Remember, when we take a square root, we get a plus or minus. So what that means, right, our domain is going to be the set of all x's and y's such that y does not equal negative x and y does not equal x. I'm going to list it twice. All right. So that's the only restriction. Hopefully you know what that is. Those are two lines right down the middle, one going up, one going down. It's our whole diagonal. So my graph is actually the whole graph except for those two lines. So this is how I'm going to graph it. You'll probably do a little different in pencil, but I'm going to graph the whole plane. All right. And then I know I can take any of those numbers I want except for, and I'm going to put this like a white line down here, and I'm going to put a dotted line to show it. But cool. So it goes right down the middle. Let me move that a little bit. Good enough. Right. And then we have this one going to this diagonal. And then what I do to show it on here, you're just going to do dotted lines. And it's not going to be too clear. It'll be clear, but not looking like this. Let me change the dotted line to some smaller. So I'm going to put my dotted line there to show that that line is not included in my domain. All you would do if you were on a test, right, you would draw those two dotted lines and then you'd go shade with solid, right, not the dots. But you just shade it like that to show that it's all four areas. Okay, so there's our domain. We graphed the domain. It's everything on this graph except for the dotted lines. Right, not too bad. Just using algebra, no calculus still. All right, let's take a look. A couple more, making our difficulty a little more difficult. All right, so I see two variables, so that tells me the graph is 3D, but the domain is going to be the same number, so it's 2D. Okay, I see a couple things. I see ln of y minus x. Hopefully you guys know that the ln, you can only take it if it's positive. It can't even be 0. It can't be negative or anything. So this tells me that we know y is strictly greater than 0. All right, so I'm going to graph that. It takes a dotted line on the graph, right? Oh, I messed up. It's not an x or a 0. It's an x, right? We're going to add that x over. Right, so I'm going to do a dotted line. Actually, this gets pretty snug in here, so I'm going to go ahead and recreate my axes, making every other one 1. I just want a little more room. Okay, so y equals x. That is a dotted line right down the middle, right? And then it says y is greater than, so we shade above. So we shade above the line. All right, now let's take a look. I'm going to do the other one in blue because we're going to graph it as well. The denominator has an x minus y plus 1 inside the integrand. Usually that can be this, right? But since it's in the denominator, it can't be 0, so I'm going to get rid of that. If I solve this for y, I get y is less than x plus 1. All right, again, that's a dotted line at 1. So we get that line. Get my dotted line off. And this says y is less than that. So if I graph this, we get all the stuff that's less than. Right? You can see the overlap there. It's the dark portion. That is our domain. So what this means, and it's kind of cool, is we have an xy plane here on our graph, right? This is x, that is y, and z is coming up this time. So the coming up, xy, the only places this function is actually evaluated is in that strip. So there would only be values coming up or down directly above or below that strip. The blue and the orange, when they're by themselves on this picture, there's nothing there. You can't even plug those in because you couldn't evaluate your square root, you couldn't evaluate your logarithm. One or the other would cause an issue. So this graph only exists in that single strip right down the middle. I'm going to show you a grapher at the end of this lesson, and there'll be 3 parts. In part 3, I will show you a grapher, a 3D grapher. That way you can go and plug these in, and you can take a look and see what they look like. Okay, we didn't state the domain, so we need to do that. The domain is the set of all ordered pairs such that, and then do you see the double y there? So what I'm going to do is I'm going to say x is less than y, which is less than x plus 1. If you look, that's captured in both of those. You could also just write both down and put an and. That's fine if you want to play it safe. I totally get that. But there we go. There's our domain. It's all the y's between those 2 lines. There's only x's and y's we can plug in. Right. We have one last example here, and it looks pretty nasty, and you guys are going to see me try to draw a sphere, which I'm horrible at. Right, I have that. This tells me that this is a 4D graph. So we can't graph this anyway if we wanted to. I guess you could try, whatever that's going to look like. But the domain is 3D. So we have a domain that's 3D. I know that the inside there, because it's the square root, the inside must be greater than or equal to 0. It can be 0. It's not in a denominator this time. That's 9 minus. I'm going to go ahead and add all these together and just minus it at once. This is so I can take it to the other side. So this tells me that, and I'll get rid of the parentheses now, x squared plus y squared plus z squared is less than or equal to 9. Okay, hopefully you know what that is. We've done a lot of work this semester, really quickly though. That is a sphere. Right, this makes sense. 3D domain. Our domain is that sphere. So when we graph this, let me bring this graph up here. I'm going to try to graph a sphere. I am horrible at this with an iPad, much better with a pencil. But this is a sphere with a radius of 3. So I'm going to put a radius of 3 on each one of these. And then we're going to attempt to draw a sphere. So the first thing I'm going to do is draw the circle that's on the XZ plane. All right, so we try. It's really tough with this iPad. I get a lot of squiggles. Do your best. So that's supposed to be a perfect circle on the XZ plane. Then I have a circle here. There, right? It's looking pretty bad. Sorry for I can't hold my pencil straight enough to do that. So that is on the XY plane. So the last one we're missing is the ZY plane, which just gets us a few of these boundaries. I think that's good enough for a sphere. I can tell. This says that the domain has to be that sphere or less. So I am going to shade the inside of this sphere. So it's if you pick a point on the sphere or inside the sphere, you can plug that into your function, right? You could take x, y, and z from the sphere, wherever you want to pick in the sphere, and pick your favorite point. And if you plug the x, y, and z into this, you'll get a w out. You'll get another number out. Now we didn't list our domain. Our domain is the set of all x and y's such that x squared plus y squared, we could even put 0 to, that it's greater than 0. It's kind of obvious, but there we go. Less than 9. So it's any point in that sphere. It's kind of cool. Pick any point inside that sphere, it will work in our function. You pick a point outside that sphere, it will not work in our function. All right, I have one more. I think I just said I had one more, but it's because my notes are on the same page. But the next example, we'll end with this one, this video with this one. I have my function there, and okay, I see 3 variables, so that means that it is 4D graph, which means I can't graph the graph itself, but it has a 3D domain, so I can graph that. All right, so I know a couple things. 4 minus x squared minus y squared, that's in a radical, so it can be 0 because it's in the numerator. We know we can rewrite this like the other problems. And then that tells me that x squared plus y squared is less than or equal to 4. Now, you're maybe wondering, oh, that's a circle, right? Kind of. This is in 3 dimensions. So this is actually a cylinder. So it's a circle in the xy plane, right? That's our trace there. And then we have that circle trace all the way up and down along z. So we have that. Okay, that's one part of my domain, is that I have to have that circle within 4. I also have to have z minus 3. That can't be equal to 0. It's in the denominator. That tells me z can't equal 3. We'll handle that in the last. Okay, so let's draw this picture. So we have a circle trace of radius 2 on this plane. So let's draw this. I'm going to actually do it with dots and everything. All right, so I have that. Okay, so we have that, and it's a cylinder. So what that means is that I am actually, and you're just going to redraw it, but I just put this everywhere going up. I'm going to try to line them up. Actually, let's do something first. I know this cylinder is going to go, let's just delete that. Just go backwards. Okay, so I'm going to draw straight up and down lines to make my cylinder. All right, so I have this straight up and down line. Usually what I do is I make one straight up and down line on here, and then I copy. You're just going to redraw on your pencil. Just use a ruler. There we go. So I'm going to put these lines on here to show some three-dimensional movement here. Not movement, I guess, shape. I also can do a dotted line like that. I can just paste. Style. Move it. Okay, and I can throw that behind to help with our shape. If I can grab it. There we go. Right, and then I like to grab this middle part. You're going to redraw that circle that's in the middle. Just move it up. Let's use lines. Do this. Go ahead and copy that. Again, okay, and then I take this and I'm just going to put it on there so I can see the shape. All right, so I have that. I also have one below. I want to make sure it is known that it goes up and down. Right, and then let's deal with this this part here that we really haven't talked about. Right, z minus 3 will give us that z can't be 3. Okay, so I'm going to shade this in because it does tell me that my domain is everything less than that cylinder. So I get everything here. Do my best to stay in the lines. But what that z equals 3 does is this just says we don't have a disk at 3. So what I'm going to do is I change this. Oops. I'm going to find a way to show this. Make that white. And then I'm going to have it go through at 3. So we get like this disk here, right, at 3. And this disk is going to be removed from that cylinder. So I have that whole cylinder there, but this z can't be equal to 3, cuts that disk out. So I can choose any point for this domain in that cylinder, on the cylinder, inside the cylinder, except for if z equals 3. Hopefully that makes sense to you. The domain for this, we just write down those things, right? So it's the set of xy's such that, okay, x squared plus y squared is less than 4, and you just write this to the side, I just ran out of room, z cannot equal 3. We just have both. All right, so that's how you find domain of a multivariable function. The next video is going to focus on actually graphing these functions. Please note that we haven't graphed these 3D functions. We are only graphing the domain so far. If it's a 4D function, obviously we can't graph it. We can think about it. We're not even going to go that far in this class. But the next couple of videos will focus on graphing and then focus on some other type of curve called a level curve.